So the talk will be recorded, as well as any questions that you ask during the talk and immediately after the talk. If you don't want to be recorded, I'll stop the recording at some point, but the discussion will go on. If you haven't been here before, let me just explain briefly how this works. So I'm going to keep the chat is basically off. You can chat only to me. So in this way, you can perhaps ask a question if you like, or you can report some weird goings on if someone's not doing what they're supposed to be doing. If you want to ask a question during the talk, we do encourage this. We like interaction. It's always more fun when people are interacting. So please raise your hand and I'll stop Joel and you'll get to ask your question. And the other thing is we like to encourage people to keep their camera on if possible, because it's always nice just to flick through and see who's around and see people's faces. Okay, so without further ado, we welcome this week Joel Ouaknine, and he'll tell us about holonomic techniques, periods, and decision problems. Go ahead.
Thanks very much, Pavel. Thanks for the invitation. This is work in progress, very much work in progress. So feedback and questions are super welcome. Do feel free to interrupt, as Pavel explained. And if you have other suggestions or then comments and so on, we would be delighted to hear them. So this is joint work with, you can see several people. So some of them are postdocs, some are collaborators like Ben Worlds in Oxford, and there's even somebody from South Africa in the mix. So let me start with this quote of Don Knuth, which you may or may not agree with. So the quote is, science is what we understand well enough to explain to a computer. Art is everything else we do. And I think this resonates certainly with certain computer scientists, where if you're trying to develop algorithms to do certain things, I mean, certainly will not resonate with everyone. But as far as holonomic techniques are concerned, I think this quote sort of really gives the spirit of what we're trying to do. So before I explain what these things are, let me just ask a question. Here's a bunch of, I list a bunch of topics here and ask, what do all these things have in common? So I won't read them out. I'll just let you sort of, cast your eye over them. But you can see there's quite a wide variety of, different things. And by the way, I shamelessly stole this from a talk by Cyril Banderier. So the answer is that all of these things depend in some manner or other on holonomic techniques. So let me, if you've never heard what they are, then you've come to the right place. I will explain what they are, and I will start with just a simple example. So suppose you're being asked to prove the identity that you see on the screen. So the summation of these square of these binomial coefficients is equal to 2n choose n. And you're asked, how can I prove this? Well, one way you might do it is to argue as follows and to say, well, on the right-hand side, I've got the number of ways to choose n letters amongst 2n letters, right? 2n choose n is that. And you're going to choose n letters amongst the an, and sorry, you're going to choose n letters amongst these 2n letters, an, a1 to an, b1 to bn. And the ways there are to do this is obviously 2n choose n. And another way you can approach the choice of these letters is you can say, well, I'm going to choose k letters amongst the an, and there's n choose k ways to do that. I'm going to choose n minus k letters amongst the bn's, and there's n choose n minus k ways to do that. So the way they are to choose n letters amongst these guys for a particular k is the product of these two. And then I'm going to sum over all k. And so obviously I'm counting the same thing on the left and on the right, so they must be equal. And now, of course, I've got the sum of n choose k times n choose n minus k, but by symmetry, this is really the sum because n choose n minus k is the same as n choose k. So this is the sum of n choose k squared. And by the reasoning above, this is equal to 2n choose n. Okay, so I've proven this little identity. I think this is a cute little proof. And Don Knuth would call this, oh, this is art. Okay, then it's art and not science in the sense that it's not clear how you might generalize this. If I put a cube instead of a square, then it's not clear at all that this little argument would work. How could we do this systematically? So let me illustrate using a completely different approach. So if you look at the left-hand side, this is an expression that depends on n. So for every natural number n, this will be a number. And the right-hand side is the same thing. So I'm going to label the sequence of numbers I get on the left-hand side. I'm going to call this the sequence un, u sub n, and the v sub n for the sequence on the right-hand side. And the high-level strategy is I'm going to find a recurrence relation for the sequence of numbers un, find a recurrence relation for the sequence of numbers vn, combine to obtain a recurrence relation for the sequence un minus vn, and then finally verify that the sequence is identically 0 by checking the initial values. And then by induction, because I've got a recurrence, by induction, this will be true for all n. And I will therefore have shown that the left-hand side is identically equal to the right-hand side. Okay, so let's see how this works in practice. So the right-hand side is Vn, so that's 2n choose n. So you have the expression there, 2n factorial over n factorial squared. And Vn plus 1 is this, which if I expand gives me that, which if I expand gives me this. And here you can see you've got the 2n factorial, the n factorial, and so you have the little term Vn lurking in there. If I put everything together, I see that n plus 1 squared times Vn plus 1 is this expression times Vn. And I have to tell you what the initial value is. So V0 is 1. And you can see this is a first order holonomic recurrence. So why is it first order 1? It's order 1 because every term in a sequence depends only on one previous term. So Vn plus 1 only depends on Vn, so it's order 1. And it's, okay, and the coefficients are actually these polynomials in it. Let's try to do the same for the left-hand side. So I write un to be the left-hand side. And now if you try to express un plus 1 in terms of un, or un plus 1 in terms of un and un minus 1, you're a little bit stuck. You can try it with a paper and pencil after the talk, and you find that, oh, it's not so easy. But if you look at the summand, this n choose k squared, this actually turns out to be sister Celine summable. And I will explain what this means later. That means you can use Zalberger's algorithm to automatically derive a recurrence for un. And it turns out the recurrence you get is the following. You get n plus 1 times un plus 1 is 4n plus 2 times un. So you have, again, an order 1 recurrence, and you have u0 equal to 1, okay, by inspection. So if we put everything on the same slide, so on the left-hand side, I've got a recurrence for the un. On the right-hand side, I've got a recurrence for the vn. Both of these recurrences are order 1. So in other words, un and vn both satisfy what are called the holonomic recurrence relation, so linear recurrence relation, but with the polynomial coefficients of order 1. And therefore, the difference, or the sum, or the difference of these things will satisfy a holonomic recurrence relation of order 2. And this is proven, this is a simple linear algebra argument. And therefore, I only need to verify, I don't even need to compute what this thing is, although I could. I only need to verify that u0 minus v0 is 0, and u1 minus v1 is 0. And after that, because the un minus vn satisfies a recurrence of order 2, I know by induction, because the first two terms are 0, that every term will be 0. And I have therefore proven my identity. Okay. So let's look at a slightly more complicated example. So in 77, Roger Appéry produced what has been described as a sensational proof of the irrationality of zeta of 3. So this is the Riemann zeta function, and zeta of 3 is this expression here. And the critical ingredient that Appéry used are the so-called Appéry numbers, which are defined as this binomial expression, so a little bit more complicated binomial expression. So these are the AN. And Appéry showed or claimed in his talk, he presented this talk where he didn't really give any proof. He just sort of asserted one thing after another. He asserted that these Appéry numbers obey the following recurrence. And you can see the recurrence is an order 2 recurrence. So the AN plus 2 depends on AN plus 1 and AN. And the coefficients are these cubic polynomials. So here you've got n plus 2 cubed, here you've got this cubic polynomial, and here you've got this cubic polynomial. And he was asked about, well, how do you know this recurrence hold? And or where did you find these recurrences? And he answered cryptically, is, oh, they grow in my garden. But of course, number theorists wanted to prove. So van der Poorten worked with another number theorist, Henri Cohen, and they tried to prove this identity that these Appéry numbers obey this holonomic recurrence. And van der Poorten writes, neither Cohen nor I had been able to prove the above in the intervening 2 months before the International Congress of Mathematicians. After days of fruitless effort, the specific problem was mentioned to Don Zagier, and with irritating speed, he showed that indeed the sequence satisfies the recurrence. This more or less broke the dam, and the rest of the proof was quickly conquered. It's interesting that it stumped 2 very strong number theorists for 2 months. Now, poor van der Poorten was unfortunately a couple decades too early, because if he'd come a little bit later, instead of using Zagier, he could have used Zalberger, and in particular Zalberger's algorithm, not only to prove that the recurrence holds, but in fact to derive it from scratch. So here's a picture of Doron Zalberger with a fitting T-shirt. And if you use, for instance, if you use the sum tools package in Maple and use the sum recursion command, So here's this binomial nk squared, binomial n plus kk squared, etc. This is the expression for the a priori numbers. And if you plug it into Maple, completely automatically you get exactly the a priori recurrence. You don't even have to guess it. You can get it automatically. So it's interesting. I mean, it shows you that these algorithms are not completely trivial because these very smart number theorists were sort of stuck with this for quite some time. Let's look at a third example, and this time a continuous example. Suppose you're asked to prove that sine of 2x is equal to 2 sine x cos x. So one of these, trigonometric identities. And of course, you may ask, well, what am I allowed to assume? So let's assume just the differential equations that govern sine x and cos x. So the double derivative of sine x is minus sine x, the same for cos. And sine and cos, of course, differ in their initial conditions. So sine 0 equals 0, sine prime of 0 equals 1, and for cos is the other way around. So we're only going to assume what's in the box, as well as the chain rule. And now how are we going to prove this? Well, the strategy is the same. We're going to label the left-hand side f of x, label the right-hand side g of x. We're going to find a differential equation for f of x minus g of x and conclude that is identically 0. So how does this work? So the differential equation for f of x by the chain rule and what's in the box is there. So f of x satisfies the second order linear differential equation. And g of x, you just look at g of x and you say, it's the product of two functions, each of which satisfies a second order linear ODE. So g of x, again, by simple linear algebra argument, g of x must have order at most 4, meaning that g of x must obey a linear differential equation of order at most 4. So this is straightforward. And therefore, the difference, f of x minus g of x, must satisfy a linear ODE of order at most 6. Okay, and now all you need to do is verify that h of 0, h prime of 0, h double prime of 0, all the way up to h to the 5 of 0. So you have 6 things to verify because it's order 6. They're all 0. By the way, you verify these h double prime, h triple prime, you immediately derive them from what's in the box. So you can verify these things. And then you can invoke the Pinkards theorem to say, well, there's a unique solution. And because the 0 function satisfies this differential equation, because it's 0 on all its first 6 derivative, including 0th derivative, then it must be identically 0. So you conclude that h of x is identically 0. In other words, that f of x is identically equal to the g of x. Okay, any questions on these examples? Okay, good. So let me define these things a little bit more formally. So I'm going to define holonomic sequences and holonomic functions. So a sequence un of real numbers is holonomic, or also known as p-finite or pre-recursive, if it satisfies a linear recurrence relation with polynomial coefficients. So you have univariate polynomial coefficients with rational.
So can I ask a question? Mm-hmm. These polynomial coefficients, they can be any order.
Absolutely.
Okay.
They can be any degree, you mean?
Yes, any degree.
Yeah, any degree. That's right. So, but later we will see, sometimes we restrict the degree in some particular cases. But yes, in general, they can be absolutely any degree. So you have these univariate polynomials with rational coefficients, and the term un plus, so pk of n times un plus k is a linear combination of the previous k terms in the sequence where the coefficients are these polynomials evaluated at n. Okay, so you have this equation. So any sequence un that satisfies this is holonomic. And there are many examples of holonomic sequences, are actually quite a rich lot. Factorial numbers, Fibonacci numbers, harmonic numbers, Perrin numbers, Motzkin, Catalan, a priori numbers, etc. And also the Taylor coefficients of many functions. And this is not we'll see later, this is not a coincidence at all. But just as an example, suppose you look at the Taylor expansion of sine x, so you have it here. Now, if you look at the sequence of coefficients, well, all the even degree terms have 0 coefficients, so it's 0 in every even position. And all the odd positions, then you have the sign alternates, and you have 1 minus 1 over 3 factorial, 1 over 5 factorial, and you can very easily see that the recurrence, this holonomic recurrence of order 2, is n plus 2 times n plus 1, so quadratic polynomial. Times un plus 2 is minus un, and then you just need to give the first 2 values and you get the sequence of coefficients for sine x. Now, according to Emmanuel Cowers, approximately a quarter of the sequences in the OEIS are holonomic, but of course there are many non-holonomic sequences. So here are just some examples, 2 to the n, log n, the Bernoulli numbers, the prime numbers, so on. Now, holonomic sequences enjoy some very nice closure properties. So if UN and Vn are holonomic sequences, then their sum, their product, their pointwise product, their shift, the sequence of partial sums, and the Cauchy product, which is what you do when you take product of a power series, are all themselves holonomic sequences. And so this makes it a very good class for computer algebra because you can manipulate them in this very nice way. And one thing that should be made clear is that all these operations are completely effective. So if you're given the recurrences for these things, UN and Vn, then you can mechanically elicit the recurrences for all these further sequences. So in terms of algorithms, if you want to do some algorithmic manipulation on holonomic sequence, of course, a holonomic sequence in and of itself is an infinite object, but it can always be described in a finite manner. You only need to provide the recurrence relation with finitely many initial values. And now the result is, given two holonomic sequences, UN and Vn, with initial values in, here I wrote the algebraic numbers, but with some set in some ring in which you can make comparisons, then the equality problem or the identity problem is UN identically equal to Vn is a decidable problem. So the slogan is equality of holonomic sequences is a decidable property. So let me now say a few words about holonomic functions. So now you've got a function, continuous function from some interval I of the reals into the reals is holonomic or d-finite, differentiably finite, if it satisfies a linear differential equation with polynomial coefficients. So you have polynomial coefficients now of a continuous variable x with rational coefficients. And the differential equation that f is required to satisfy is of the form p0 of x times f of x plus p1 of x times f prime of x plus dot 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 plus pk of x times the kth derivative of f at x equals 0. And examples of holonomic functions include all algebraic functions, sine x, e to the x, log x, and then more complicated things like Bessel functions, hypergeometric functions, elliptic integrals, what have you. And again, according to Cowers, approximately 60% of the function in this handbook of mathematical functions are actually holonomic. They have nice closure properties, so you can add them, you can multiply them, you can take indefinite integral, differentiate them, and also compose with an algebraic function in this order. So if A is an algebraic function, f of A of x is holonomic, assuming f is holonomic. And again, all these operations are effective. From the differential equations for f and g and the initial values, you can derive the corresponding data for all of these operations. So now from the point of view of computing, let I be an interval, and without loss of generality, assume that zero is in this interval. So I contains 0, and if not, then you perform a shift. Now, to define a holonomic function, you need to provide the differential equation together with finitely many initial values for f and its derivatives at 0, provided that 0 is not a root of the polynomial coefficient of the highest order term of the differential equation. So this is a side technical condition. It's without loss of generality because this polynomial will have only finitely many zeros. So in an interval, because you have infinitely many values, you can always find one where it's not a 0. And let's just assume that this is satisfied. And now you can show that if you've given two holonomic functions f and g over the same interval with initial values in some ring in which you can make comparison of values, then the equality or the identity problem is f equal to g for all values is a decidable problem. So again, equality of functions, of holonomic functions is a decidable thing. And now we come to what I call the fundamental theorem of holomy theory. So unfortunately, nobody else calls it the fundamental theorem, or nobody else has thought to do this, even though, by rights, this is, there should be a fundamental theorem and it should be that. And so let me tell you what it is. But I'm trying to start a trend, okay? I'm just saying I'm the only one calling it that now, but hopefully this will change. So if UN is a holonomic sequence, then if you form the generating function, the sum of UN next to the n, that will be, as a function, this will be a holonomic function. And conversely, if you take a holonomic function, its sequence of coefficients, the sequence of coefficients of its Taylor expansion will always be a holonomic sequence. And these transformations are completely effective. Okay, it's not a very hard theorem to prove, by the way. The fact that I call it a fundamental theorem is not because it's a particularly difficult theorem, but just because it's so powerful and useful. We'll come back to this later.
Can I ask a quick question?
Yeah.
And I guess this theorem is kind of the formal way of passing, because when you started the talk, you were talking about sequences, then you launched into functions. So the machinery here tells you how to go between the two, right?
Yes, absolutely. Absolutely.
Because the sequence of the coefficients of the generating function is a sequence, and then this theorem passes you between these two worlds.
Yes, absolutely. Yeah, you're absolutely right, Pavel. Now, it should be said that not all holonomic functions have Taylor expansions. I mean, the famous function e to the, minus 1 over x squared is holonomic, but doesn't have a Taylor expansion. Or if you just take square root of x, it's a holonomic function, but it doesn't have such a Taylor expansion. But the theorem is still true. I could come back to this, but you're absolutely right. This is a way to move from the discrete to the continuous and conversely, and it will prove to be very useful later on. And just as an example, if you take the Fibonacci, the classical Fibonacci sequence, 0, 1, 1, 2, 3, etc., and you plug it in, you form the generating function, so you plug it in here, then the function you get, it's always going to be a rational function if you start with a C finite function like Fibonacci, is given by x over 1 minus x squared. And you can see this is, of course, a holonomic function. It obeys a first order differential equation. It's a one-line derivation. It's very simple. It's interesting because the Fibonacci sequence obeys a second order recurrence relation, but the function here obeys a first order differential equation. So the add equation is not sort of, these things move around a little bit, but okay. We'll see more examples. Let me just briefly talk about the history of holonomic techniques. So the absolutely simplest, non-trivial example of a recurrence of a holonomic sequence that you can think of is the following. So b times un plus 1 equals a times un. And the nth term, of course, can be written in explicit form. It's going to be a over b to the n times whatever value is u0. That's a geometric progression or geometric sequence. And that's, I think this was known by many people for many millennia. But now if you replace the constants a and b by polynomials in n, so b of n times un plus 1 is a of n times un, you don't get a geometric progression, you get a hypergeometric progression or sequence.
Joel, can I interrupt you for 1 second?
Of course.
A question coming from Peter van M. de Boas. Peter, would you like to ask it yourself?
Yes, thanks. I was puzzled by your remark that some of these functions don't have a Taylor expansion. Don't they always have a Taylor expansion in the formal sense?
Oh, they do.
Without
Absolutely.
looking at convergence.
Sorry, they do. Absolutely. I misspoke. I meant that their Taylor expansion may not converge to the functions may fail to be analytic. So they always, of course, have a Taylor expansion, but if the function is not analytic, it will not be equal to its Taylor expansion.
Thanks.
Thank you.
And you're absolutely right. If you form the formal Taylor expansion of a function, of a holonomic function, even if it's not an analytic holonomic function, the sequence of Taylor coefficients will be a holonomic sequence. So so the theorem has said that, and yeah. But these cases, I should say, are quite pathological in some sense. Where we will be using them, these pathologies will not occur. So here you have, I've defined the class of hypergeometric sequences. And if you form the power series, you get the so-called hypergeometric functions. There's standard notation for them, which looks like this. And these have been extensively studied. They include exponential function, logarithmic, many trigonometric, binomial, Bessel function, classical orthogonal polynomials. They were studied originally by Wallis and then by Euler, and then especially by Gauss, and later by Kummer, Riemann, Ramanujan, and contemporary number theorists like Poincare and Zudelin. And nowadays, the study of hypergeometric sequences and functions is a major research area within number theory. So they're extensively studied. But they are, of course, hypergeometric sequences are first order holonomic sequences. Every term depends only on the previous term. And you can study, of course, arbitrary order holonomic sequences. And the systematic study of such was undertaken by Poincare in the late 19th century. And he was mainly interested in asymptotics. And he produced many results, and several other people contributed to that line of research as well, including people like Perron, Komen, Salvi, Flageolet, Philippe Flageolet, who's depicted here. Yes, so you know, a lot is known. This has a rich history. But if you think about, again, coming back, speaking of computer scientists, if you're interested in algorithms, I would say the genesis of the algorithmic treatment or the algorithmic approach to holonomic sequences was really spearheaded by this woman, Sister Mary Celine Fasenmeier. And she made an appearance earlier. So she was a Catholic nun in Pennsylvania, who, whilst being a nun, did a PhD in mathematics and number theory at the University of Michigan, in which she developed this algorithmic method to find recurrence relations satisfied by sums of terms of hypergeometric sequences. So these binomial coefficients, of course, are hypergeometric sequences. And her method is now known as Sister Celine's method. So she published a couple of papers from her thesis, and then, unfortunately, well, for mathematics, she abandoned mathematics and went back to being a nun and doing nunly duties, I guess. But her work was picked up later continued by other people, including Gosper, Stanley, Gessel, Lipschitz, and in particular was weaponized by Zalberger in his seminal 1990 paper, A Holonomic Systems Approach to Special Function Identities. And in that paper, Zalberger elaborates the theory of multivariable holonomic systems based on Bernstein's deep theory of D module in differential algebra, where he has functions that have both discrete and continuous variables, so, many variables, and he finds a systematic way to establish identities amongst these functions in a completely systematic way. So this was truly revolutionary. And 5 years later, he wrote this book, A equals B, with two co-authors, Pitkovsek and Wilf. And Don Knuth wrote the foreword. This book, by the way, focuses only on hypergeometric identities, but so not even the full holonomic shebang, but already it's extremely useful. And so Don Knuth writes, I fell in love with these procedures as soon as I learned them because they worked for me immediately. Not only did they dispose of sums that I had wrestled with long and hard in the past, they also knocked off 2 new problems that I was working on at the time I first tried them. The success rate was astonishing. This book will help you reach new frontiers. So, these, and of course, these things are implemented. There are packages like GFun, MGFun, also packages for Mathematica that you can find. I'm not talking about, but so you can really do quite a large number of things. But the setup, the framework, of course, has limitations. And I'd like to talk about some of these limitations now. So this setup is fantastic for proving equalities, identities. But one thing that's much harder is if you want to decide inequalities, and also if you want to actually compute asymptotics. So let me illustrate this by describing 3 problems of that nature. So the first one, which I call hypergeometric inequality. So suppose you're given UN and Vn that are 2 hypergeometric sequences, and you want to know, is it the case that UN is always greater or equal to Vn? For all n, UN is greater or equal to Vn. So maybe these things count combinatorial objects, and you want to say that I always have more of the first kind than of the second kind or something. The second problem, the positivity problem, which is a generalization of the first, says, well, let UN be holonomic sequence. Is it the case that for all n, UN is greater or equal to 0? So you can reduce hypergeometric inequality to this. And the third problem, which I call the minimality problem, asks, let UN be holonomic sequence. Is it minimal? So I've not yet defined what minimal means, but if you want to, get a picture in your mind, you could ask, does UN tend to 0 as n tends to infinity? What's interesting is that the punchline, I give away the punchline, is that none of these problems are known to be decidable. Okay, even if these are sequences over, the rational numbers or something. So none of these things are known to be decidable, but we have a number of, partial results and I think some interesting developments. So let me try to explain what these things are. And perhaps one thing to point out is that in the first part of the talk, I was talking about identities, and this had a very algebraic flavor, whereas now I'm looking at problems that have a much more analytic flavor because I'm looking at inequalities and asymptotics. There's an interesting anecdote by the French mathematician David Mador on algebra versus analysis. So he writes, I was once dining at the IHES, it must have been in '96, and I happened to be seated right next to I.M. Gelfand, who is depicted here. When I said I wanted to become a mathematician, he asked whether I preferred algebra or analysis, and I said algebra. I don't understand why people want to study algebra, replied Gelfand, because in algebra, you write A equals B. But if A equals B, then A and B are the same thing. So you're writing A equals A, and what's the point of that? Well, I'm not as smart as Gelfand, so I wrote my PhD in algebraic geometry anyway. Now, what's interesting is the title of this famous book by Zalberger and co-authors is actually A equals B. Anyway, so I like this anecdote. I think it's kind of funny. So let me try to explain some of these things again through some examples. So consider the Fibonacci recurrence equation. I think everybody knows this one. So xn plus 2 equals xn plus 1 plus xn. Now, if you have a sequence that satisfies this equation, So any sequence satisfying this equation is a solution of the recurrence. So of course, the classical sequence 0, 1, 1, 2, etc., that is one solution. But of course, if you start with two different values like -7 and 3, you will get another sequence, right? You will just build it by construction. And the set of sequences, of course, forms a two-dimensional vector space. I mean, it's clear if you take two solutions, you add them, again, you have a solution of the recurrence. If you take a solution, you multiply it by constant, you have again a solution. And the reason it's two-dimensional is that once you fix the first two values of the sequence, you have fixed the entire sequence. You have only 2 degrees of freedom. And now I can define what minimality is. So a non-zero solution UN, so sequence, is minimal if for any other linearly independent solution Vn, we have that the ratio of UN over Vn tends to 0 as n tends to infinity. Now, this is fully general, but in the case of the Fibonacci sequence, recurrence rather, we know that, I think most people know that the general form of a solution to the Fibonacci recurrence can always be written as a times phi to the n plus b times phi bar to the n, where phi is the golden ratio, phi bar is the Galois conjugate of the golden ratio, and a and b are arbitrary real numbers. Now, if you look at this, this set of solutions, so the golden ratio is absolute value greater than 1. So if a is not 0, this term here will diverge to plus or minus infinity, whereas phi bar is absolute value strictly less than 1. So this term will always converge to 0. So now it's very easy to see what the minimal solutions are. The minimal solutions are those that have precisely a equals 0. Okay, and let's actually see this in practice. So here's the vector space of Fibonacci equation. So this is R squared, but I want you to think of any point in R squared as a sequence that satisfies the Fibonacci recurrence. And I identify the sequence by the first two terms of the sequence, U0 and U1. So for instance, the classical Fibonacci sequence that begins with 0, 1 sits at coordinate 0, 1 and denotes the entire sequence. Now, here is phi bar. It has value minus 0.6 something or other. And the subspace of minimal solutions is given by this blue line. So in particular, the sequence that starts 1, phi bar is a minimal solution. And one very important thing is the so-called critical ratio, which we denote by mu, which is the slope of this subspace, which is actually equal to phi bar. That will play an important role later on. Okay, so let me just see a couple more examples with this Fibonacci recurrence. So here I'm going to plot a Fibonacci solution against n. Okay, so this is un against n. And suppose I start at 1, phi bar. So this is meant to be a minimal solution. And indeed, I have 1, phi bar, then so on. And I can see as n tends to infinity that I very quickly converge to 0. What if I were to start at 1, something a tiny bit above phi bar? Then perhaps unsurprisingly, I mimic the minimal solution for a little bit. And then around 15 or so, I start diverging to plus infinity. And if I were to start instead at 1, phi bar minus something a little bit below phi bar, then I would, mimic again for a while and then go to minus infinity. Okay. And so whether I go to plus infinity, 0 or minus infinity depends on whether the ratio of my first two terms is equal to phi bar, is bigger than phi bar, or is smaller than phi bar. So in other words, anything above the blue line will go to plus infinity. Anything on the blue line will tend to 0, and anything below the blue line will go to minus infinity. Okay, so let's look at another example. So with the a priori numbers again. So recall the a priori recurrence equation, this cubic order 2 recurrence. Now, the a priori numbers that were defined using this binomial, this sum of binomial expression, numerically, they have the first two values are 1 and 5. And once you've defined 1 and 5 and you have the recurrence, the other values are uniquely determined. So that's a solution to this recurrence. Another solution begins not with 1 and 5, but with 0 and 6. And now, in fact, you see you don't have integers. The reason you have rational numbers rather than integers is when you calculate the new term, you must divide by n plus 2 cubed. So this is how you get these denominators. And now any linear combinations of these two solutions, of course, is again a solution of the a priori recurrence. So if you form un to be the sequence bn minus zeta of 3 times an, by linearity, un is also a solution of the a priori recurrence. And the punchline of a priori's proof is the fact that un tends to 0 fast as n tends to infinity and through elementary means, that implies that zeta of 3 cannot possibly be a rational number, okay? And because it has approximations that are just too good. An immediate consequence of this is that UN is a minimal solution. And now if you ask yourself, well, what is the critical ratio? So to compute a critical ratio, you have to compute the ratio of the first two terms. So U1 divided by U0. So you just plug it in and you find that a critical ratio is this sort of funky number. It's 5 minus 6 over zeta of 3. Now, zeta of 3 is, well, we know it's an irrational number by a priori, but it's, most people think it's a transcendental number. So you can see here, for this recurrence, the critical ratio is ostensibly a transcendental number. So if I want to know, if I give you a value, the first two values of a sequence, and I tell you, is the ratio of these two things equal to critical ratio, you start having to compare real numbers. And of course, we know that this can be a dicey sort of thing to do. Let me just show a little amusing example. So suppose I ask you whether this infinite sum here is equal to square root of pi. So, you look at this and, okay, you could do some numerical calculations and so on. But it turns out this equality is a false equality, but the two sides agree to over 42 billion digits. This is taken from this entertaining paper, Strange Theories and High Precision Fraud by the Borwein brothers. And so basically it shows that comparing real numbers, as we know as computer scientists, this can be complicated, but there is a class of numbers for which it's conjectured that you can compare them. Comparisons can be done. So these are periods. They were defined by Kontsevich and Zagier. So here's Don Zagier now with a beard, and Kontsevich was his PhD student who won the Fields Medal in '98. And you can read the definition, or you can just look here. So what's a period? The period is an integral of an algebraic function. So G is an algebraic function over a semi-algebraic set. So periods include all algebraic numbers, but many other numbers beside, like pi is a period, for instance. And in fact, this notion goes back further. It goes back to Grothendieck, who did not define these things formally, but he formulated these conjectures, such as the Grothendieck period conjecture. Now, I think I'm a little bit short on time, so I won't read it, but this is fascinating. It's perfectly incomprehensible. It talks about the RAM cohomology and all kinds of crazy things. If you can look, at some point, go and read this. I have the greatest admiration for people who understand these things. But thankfully, an essentially equivalent conjecture was formulated by Kontsevich and Zagier. It's a little bit easier to manipulate. And it says that it's decidable whether two given periods are equal or not. And in the sequel, we use this form because it's a bit more convenient than Grothendieck's. Now, there are also generalizations of this. Let me not talk about this. So let me just now walk you through the last example, which is how, if you are interested in things like positivity or minimality of a sequence, how do you go about it? And I'm just sort of at a high level explaining how one might try to go algorithmically about this. And I'll be stating some sort of classical results as I go. And just sort of bear with me. So this is sort of simplest example I can think of that is not trivial. So take a second order degree 1 recurrence. So second order because xn depends on the previous two terms. And degree 1 because all the polynomials involved, in answer to, so related to what Pavel asked before, or somebody else asked before, all these polynomials are linear or affine polynomials. So absolutely simplest possible case. Now, and my sequence, because the paper is written this way, it doesn't start 0, 1, it starts with -1, u -1, 0. So let's just go with that. So given two initial numbers, u -1 and u0, let's say they're rational or real algebraic, we want to decide whether the full sequence is minimal or whether the full sequence is always positive, right? We want to decide, these are the kind of questions we want to decide. And so here's how we would proceed. So for each n, you can build a characteristic polynomial, which is, given, polynomial in Z, and calculate the roots, little lambda n and big lambda n. And then you can show that the roots, the little lambda n tend to 1 and the big lambda n tend to 2. And now there is this classical Poincare Perron theorem that says, look, it's a completely general theorem. It tells you for any solution un of the recurrence, the ratio of consecutive terms will either tend to the small lambda or to the big lambda. These could be repeated roots, by the way, they could be complex, but this result in some form or other, there are corresponding results for these things. If you think of the Fibonacci sequence, you know that the ratio of consecutive terms of a Fibonacci sequence tends to the golden ratio. And if you are in a minimal solution, they would tend to the conjugate of the golden ratio. So it's a similar sort of thing. And now you can see, well, what are the minimal solutions? Well, if the ratio of consecutive terms tends to 2, let's say to big lambda, then clearly the terms grow very fast. But if the ratio of consecutive terms tend to 1, they grow much less fast. So the minimal solutions are precisely when the ratio of consecutive terms tend to small lambda, okay? UN is minimal if the ratio of consecutive terms tend to small lambda. Okay, so what about the critical ratio mu? How do you calculate this? Well, there is a way to approximate it. So first of all, I've rewritten my recurrence by dividing by 2n plus 3. So I get this form of the recurrence instead. And now there is this general theorem called Pinkards Theorem that expresses mu as an infinite continued fraction of these terms as n tends to goes from 1 to infinity. So I've written the first few terms here. And numerically, you can evaluate this. This is about 0.511. And it so turns out that you can write this as a ratio of Gaussian hypergeometric function, but this is not always the case. The point I'm making here is that you can approximate the critical ratio, but in general, these infinite continued fraction, you have absolutely no way of knowing what they are. You don't know whether they converge to a rational number, an algebraic number, a transcendental number. You have absolutely no idea of knowing these things. I mean, there's a lot of studies, a lot of, people have studied these things, but we know very, very little about, the limits of these things. So if I give you two values, two terms, u minus 1 and u0, and ask you, is the ratio equals the critical ratio? You don't have a means to do this, at least not from this continued fraction expression, or at least nobody knows how to do that. So how might we proceed? Well, first of all, let me just plot the ratio of consecutive terms, un over un minus 1, against n, just to see what we're dealing with. So first of all, the critical ratio is here. The big lambda is 1 is here. Small lambda and big lambda is there. So if I start on the critical ratio, if the ratio of the first two terms is equal to mu, then indeed I will converge to little lambda. Okay, so these plots were generated with Mathematica. It's not me cheating. If I start a little bit above the critical ratio, so u minus 1 over u0 over u minus 1 is a little bit bigger than mu, then as expected, I will converge to big lambda. And here's another instance in which I start closer, so I converge a little bit slower, but I eventually get there. If I start below, I will go negative, which means one of these terms at some point becomes negative, and then I go positive, and then I converge to big lambda as expected. And likewise, if I start just below the critical ratio, I eventually become negative, then I go here, and I converge to big lambda. So you can ask the question, how do I know whether or not I am in the situation in which I'm on a minimal solution or I'm not? And if I give you two initial terms whose ratio differs from mu by 42 billion digits, you will be on this trajectory for a very, very long time before you start realizing, oh no, I'm going up or I'm going down. And for that matter, if I give you two initial terms whose ratio is mu, then you will be here forever. But you will never know for a fact that you're there, right? You will just keep calculating and say, okay, it looks like I'm converging to, but what, how do I know? So how are we able to tell, given that we only can approximate mu, whether a ratio of two terms is bigger than mu, equal to mu, or smaller than mu? And for this, we borrow a trick from analysis. So this is spelled out in German by Erich Hecke. So here's the English translation. It is the fact that the precise knowledge of the behavior of an analytic function in the vicinity of its singular points is a source of arithmetic properties. So how do we use this? Well, we form the generating function of the UNs. So here it's UN minus 1 because I started at minus 1, but it's really the generating function of the UNs. Okay, so I form this f of x equals u sub n minus 1, the sum of u sub n minus 1 x to the n. And now how can I tell whether the ratio of the UNs tend to 2 or tend to 1? This is really what I'm trying to determine. Well, if you think about it, when the ratio of consecutive UNs tend to 2, the radius of convergence of this function has to be a half. Whereas when the ratio of consecutive terms tends to 1, the radius of convergence of this function will be 1, just by the ratio test. So whether the radius of convergence of f is a half or 1 will tell me whether I initially started on the critical ratio or not. So how would we determine this? So here's the kind of the final piece of the puzzle. So I write f of x equals this generating function. By the fundamental theorem of Holonomic theory, I know that it satisfies a differential equation, which I've written here. And I can solve this using classical means, and here's the solution. So the solution, I've got square root of 1 minus x, then I've got this integral of an algebraic function in y. So you see u0 here, this is a constant, u minus 1 is a constant, and otherwise I've got an algebraic function in y, dy. And then on the denominator, I've got these rational functions in these algebraic expressions in x. And now I notice that I actually have a pole at x equals a half, because if x equals a half, this is 0. So if my function f is to have radius of convergence 1, then it cannot possibly blow up at x equals a half. But how am I going to cancel this pole on the denominator? Well, the square root of 1 minus x cannot cancel it, because when x equals a half, that's just a square root of a half. So the only way I can cancel this pole is if this whole integral is equal to 0. Okay, so I've shown that if un is minimal, this integral has to be equal to 0. And actually, you can show the other direction as well. And now if you look at this integral, well, that's the integral of an algebraic function over the interval 0 half. So that's the period. So if you believe the Kontsevich-Zagier conjecture, then this is something you can decide. You can decide if this function is a period. Now, in more complicated examples, you get exponential periods, or you get slightly more complicated expressions. But again, you invoke the corresponding conjecture to say, yes, this is something I can decide. Now, just one last observation is that we've established that you can decide if a function is minimal by evaluating some integral and deciding if it's 0 or not. What about positivity? Well, here you can see that you're going to be positive either if you're minimal or if you started above the critical ratio. And otherwise, you always will go negative. And this is a general sort of fact that you can reduce positivity to minimality. So here, you're positive if you're minimal, or if this ratio is bigger than you. This is something you can always decide by numerical analysis. And this is something we claimed you can decide through this period conjecture, if you believe it. So we have actual theorems. I'm running out of time, so I'll just go very quickly. So for second order sequences, positivity reduces to minimality. For second order degree 1 sequences, positivity and minimality reduce to deciding whether a period or a similar object is 0. You can also decide these things relative to Gabrielov-Vorobyov oracle for Pfaffian systems, and I'm not going to talk about this. And hypergeometric inequality also reduces to determining whether a period is 0 or not. Okay, so what is the outlook? Well, holonomic sequences and functions have been extremely well studied from the point of view of their algebraic properties, their identities, and so on. But what I feel has been vastly underexplored up to this point is the algorithmic treatment of the analytic properties of holonomic systems. So I've only talked about 2 properties here, minimality and positivity, or inequalities, and these are sequences. But of course, there are many other questions you can ask about holonomic sequences and also holonomic functions. And I think this is a kind of ripe for research, or as Knuth would put it, we should try to turn more of the art into science. Thank you.
Thank you very much, Joel. So I've allowed people to unmute themselves, so maybe we can start by thanking Joel for this amazing talk. So please go ahead and unmute yourself and let's clap.
Thank you.
We'll take questions now. Please put your hand up if you'd like to ask a question. Peter, go ahead.
Thank you. Most interesting.
Thanks.
Can you give us some information about the complexity of the algorithms which are under the hood here? We're referring to Zeilberger, his methods, and this method of this American nun. How complex are they?
It's a good question. So I am not an expert in these things, I must confess. I've only discovered these holonomic things a few, maybe a year ago or something. I know, so the theoretical complexity, I'm sure this has been studied, but in practice, I know these things are very efficient because, so the sister-Celine algorithm was not so efficient, and Zeilberger spent a lot of time fine-tuning his algorithms. Zeilberger really implements things. In fact, he often credits his papers with, his name and another name, which is a computer in Hebrew or something. So he implements these things. And from what I understand, if you download these packages, and not necessarily written by Albuquerque, like gfun or mgfun, and you play with these things, you get answers in fractions of seconds. So these are very, very efficient. These are not theoretical things. These are really things you can use. I must confess, I have never used them myself. but this is what I read about about these things. I don't know if this answers your question.
So you don't know whether the formal there is a formal decision on the algorithmic complexity of these problems.
I expect there is, but I must say, no, I don't know for a fact what these things are. I think I would have to look. But I mean, there's a vast literature on these things. So I assume people have looked at these things because it's such a natural question. It's just that I'm afraid I'm not able to give you an answer at this point.
Thank you.
Any other questions?
Yes, may I ask a question?
Yes, go ahead.
Yes, of course.
Hi, thank you very much for your talk. It was very interesting. I wanted to ask a very basic question. Where does the holonomic name come from? Why did you call this type of group holonomic?
So that's a good question. Yeah, holonomic. So this was Zeilberger. These things were known, I guess, they're also known, these sequences are known as P recursive and P finite, as opposed to C finite, where you have constants. And calling the sequences holonomic was really Zeilberger's idea. He wanted to unify, like I explained, he had these functions that had both discrete variables and continuous variables, like these Chebyshev polynomials, that sort of things. He proves all kinds of amazing identities with them. And he wanted to put them in one uniform framework. Now, Bernstein had developed this theory of D-modules to prove theorems in analysis about meromorphic functions. And Bernstein called his theory the theory of holonomic systems, but it was completely not algorithmic in nature. And so Zeilberger, I believe, took the name holonomic from Bernstein and called both the functions and the sequences holonomic. And I think in view of what this fundamental theorem that I want to start a trend, I think it's a great choice of terminology, because now you say, yeah, they live in the same kind of, in the same conceptual universe. But it goes back to Zeilberger, who was inspired by Bernstein, is the answer to your question.
Yes, thank you very much.
And I should say just one more thing. The engineers have a notion of holonomic, which has to do holonomic systems when they model things in robotics and so on, which has to do with degrees of freedom of their objects or something. It's a different notion, I believe. Maybe it's related in some way. I'm just not sure.
Thank you very much.
That leads me to ask a question actually about your fundamental theorem. What do I cite for that? What's the source for this?
It's a good question. It doesn't exist because how do we get it? Somebody suggested you should create a Wikipedia entry. Maybe what I'll do is, we haven't published anything on this, although we have a draft paper. Maybe what I'll do is I'll call it that in the paper. And if the paper is accepted, then you can cite that.
But are you saying that this has not been proved before? Or like...
Oh, sorry. The theorem has been proved. The theorem. So none of the first part where I was talking about these algebraic identities and so on, all of these things are not original results to me. Right. And this is all not just proven, but Zeilberger, like I explained, he was doing the multivariable thing. It's much, much more sophisticated than what I only presented something. I give you kind of a cross section of what I thought was interesting, just to give a flavor. No, I claim no originality. I only claim originality for naming things, not for proving any of the things in the first part. The second part, of course, the analytic business, this is our work. But the first part is all due to, all these various people I cited.
And I've got another kind of follow-up question. Do things become fundamentally simpler at degree 0, if you consider linear recurrence relations?
A lot of these problems do. I spent, I guess I spent several years, maybe almost a decade, working on linear recurrent sequences, basically, and dynamical and equivalently dynamical systems. And I'm still, doing a lot of work on these things. There are very hard questions there as well. But the particular question I look at, for order 2, for instance, they are, I wouldn't say quite trivial for C finite sequences, but they're a lot easier. But I think the headline result, the headline sort of problem for C finite sequences, where you've got constant instead of polynomials, is the Scullin problem. So you're given a linear recurrent sequence and you ask, does it have a 0? And that is known to be decidable up to order 4. And at order 5, it's not known to be decidable. But even order 3 and order 4, it requires this result of Baker's theorem, which was a very sophisticated.
I remember you talking about this at Southampton. It's remarkable that this is not known, right? It just sounds so simple.
Yeah, no, this is that. So there are plenty of open problems for C finite, and it's just that we're looking at this because it's also interesting. It's using some other types of mathematics, but yeah, I know it's a fascinating area. You've got open problems sort of everywhere dense, basically.
Thank you. Any other questions? Please just feel free to jump in. You're able to unmute now.
So, hi, Joel.
Hi, David.
Hi. So I wanted to ask. So, as I remember, for linear occurrences, kind of the main difficulty comes where you have several roots of absolute value 1.
Yes.
So you can't just say, oh, this root wins. So what happens there for the positivity problem?
So with a positive, you mean in the holonomic setting?
Yeah.
In the holonomic setting, the analog of roots are these little lambda n that tend to, they tend to limit. And so you do use these things. So when in example I had little lambda and big lambda, and one was dominant and the other wasn't dominant, but still it wasn't as easy as in the C finite case. It's not just I could just dispense with the positivity problem, right? We saw things where, but I am using this technology, and in this particular instance, the technology leads us to checking whether a period is 0 or not. If you do the same analysis with a Fibonacci sequence, then you find that the integral that you're looking for equal to 0 is something you can calculate. It's an algebraic number, and then you can decide if it's 0 or not. So things are just a lot easier. Does that make sense?
Well, so I guess the thing I'm a bit confused about is if both these things that your roots are tending to have modulus 1.
Oh, yes. Then you need to, the analysis, so if you look at the paper, we've put this paper in archive, we handle this case and it's different. And this is where you get the so-called exponential period. So it's a different sort of analysis. I was just trying to show the simplest possible example I could find. But of course, there are other cases to consider. You're absolutely right. Yeah, so this case is harder. Your intuition is completely correct.
Okay, thanks.
Okay, I don't see any further hands raised. So I think let's thank Joel again.
Thank you. And if you have other questions or comments, just drop me an email.
Also, right now I'm going to just finish the recording.